Hi guys, today we will talk about combined loading, what that means for you in strength of materials. It refers to the situation where a structural element is subjected to more than one type of loading simultaneously. So up to now we were talking about axial loading when we had a force, and that is the only loading which we have on the structural element. Then we have bending when we had a moment, then shear and torsional forces. So in this case, when we are talking about combined loading, we are talking about axial plus bending or axial plus torsion, bending plus torsion, or the all of them together, axial plus bending plus torsion plus shear, when we require the use of Mohr circle, von Mises circle, or maximum shear stress criteria to evaluate failure. So why this matters? Real components. So in reality, you can notice on a bridge there is trucks, then we have cars, then we have pedestrian, we have a wind, then earthquake can occur, etc. So all of these type of loadings. So understanding combined loading is crucial for designing safe and efficient structures. So also it helps us to choose the right material, cross-section, and reinforcement strategies. So firstly, when we have only one force and our element is subjected only to normal force, this leads to uniform normal stress. So we have a sigma, which is equal force over area. Then we have shear force, which leads to shear stress distribution. Now we have torsional stress, tau is equal V times Q over I times T. And then we have a bending stress, which leads to longitudinal stress distribution. And for a straight beam, we will have sigma is equal minus m times y over I, where we have for I moment of inertia and y will be the centroid. Or we have for curved beam, sigma is equal m times y, and it is divided by area times eccentricity times r minus y. So this is for curved beam. Torsional moment T leads to shear stress distribution, where we have tau for circular shaft to be T times rho, and we are dividing by J. So resultant stresses by superposition, once when we have the normal and shear stress components for each loading which are calculated, we need to use the principle of superposition to determine the resultant normal and shear stress components. 2.5 meters with 50 kilonewton per meter, which will give us only 1 force of 125 kilonewton. Since that we have here 3, 4, 5 triangle, that means that our cosine of alpha will be 0.8 and our sine alpha will be 0.6. So in this case, we need to solve the equation and to find the normal forces, normal force, shear force, and moment at point C, or internal forces, which will give us normal force of 16.45 kilonewton. Then we have a shear force of 21.93, and our moment will be 21.93 times 1.5, which will give us moment of 32.89 kilonewton. That is how we did the kilonewton meter. This is a mistake. So we have moment of 32.89 kilonewton meter at point C. So these are our internal forces. We have cross section. So for cross section, we have that area is 50 millimeters times 250, or 0.05 times 0.25 meters. For a force P, we have a normal force, which will give us axial stress, and that is sigma C is equal 16.45 times 10 on cube, which will give us Newton over meter square, and that is megapascal, 1.32 megapascal. Regarding to shear stress at point C, we will not have a shear stress because it is in the edge, and my maximum shear stress will be in the middle of the cross section. So for shear stress, our shear stress is 0. Regarding to bending stress, we have moment times C over I. Since that our moment at point C is 32.89 kilonewton meter, we will multiply with 10 on cube in order to get Newton meter times 0.125, which will be our centroid in y direction. And we are dividing everything with 0.05 times 0.25 on cube, and here is 12 instead of 2, which will give us 63.16 megapascal. So shear stress, we already said, is 0. Adding the normal stress at point C, we will have moment plus axial loading, which will be 1.32 plus 63.16, and our stress, normal stress, will be 64.5